In this video, I'm going to solve this rational inequality. So the first thing I want to do is make sure that the expression is completely factored. Now, this polynomial here is actually irreducible. I know this because the discriminant, b squared minus 4ac, is equal to 1 minus 4 times 1 times 1, which is minus 3, which is less than 0. So I know that that piece does not factor. It's irreducible. Now this is a difference of squares, which factors easily as x minus 4 times x plus 4. So I've gone ahead and I've factored completely. So the next thing I want to do is I want to find the places at which the function is 0, it zeros, and I also want to find where it's undefined. Now its zeros occur when the numerator is equal to 0. So those will occur when this is 0, so when x is 2, or when this is 0, so when x is 5. And the function will be undefined when the denominator is 0. So this is never 0 because it's irreducible, and we get places where it's undefined at x equals 4 and x equals minus 4. Now I'm going to use all of those points, the zeros, and the places at which the function is undefined in my sign diagram. So I've gone ahead and put them all on the sign diagram. Now I indicated these points with dotted lines because they're actually vertical asymptotes, and I know that the function is undefined at those points. They're not in the domain of the function, so that they can't possibly be part of my solution. On the other hand, I've indicated the 2 and the 5 with closed circles since those are zeros of the function. Now I'm going to go ahead and try to find the sign on each of these intervals. So I have 1, 2, 3, 4, 5 intervals that I need to consider. Now there are a couple of ways I can do this. One way I can determine the sign on each of the intervals would be to take a test point in the interval and plug it into the function and determine what the sign is. Another way I can do it is by looking at the coefficients of each of the x in each of the linear factors on this interval, and that will tell me the sign of the linear factor on this interval. So I'm going to try that method. So first of all, I'm going to look at the 5 minus x cubed. Now I know that the coefficient in front of the x is negative 1, so that tells me that that particular factor is going to be negative on that interval. So I've got a negative linear factor and it's cubed. Next, if I move over to the x minus 2, I know that this is going to be positive because the coefficient in front of the x is positive, and then I can square it. So that's going to be a positive squared. On the denominator, I'm looking at these factors down here. I know that this one is going to be positive and this one is going to be positive. So I get a positive times a positive. And finally, this last factor, that's an irreducible polynomial. And so it has no zeros. Its sign is always the same. And if you want to think about this, you could take, say, a test point on this interval like 6, and when you plug in the 6, you know that this is going to be positive. So now I know that I have a positive here. And overall, what do I have? Well, I have a positive times a negative, which is negative over a positive, and a negative over positive is negative. So this function is negative on that interval. Now another way you could do this, you could determine the sign just by taking a test point on the interval. And we're allowed to do that by a theorem that we call the intermediate value theorem, which we'll learn soon. So I could, for instance, take the test point 6, and when I plug it in, I know that this is positive, and 5 minus 6 is minus 1, and then minus 1 cubed is negative. And I plug in 6 here, I get positive. Here, I get positive and positive, so I'm going to get the same sign. So you can always do that. You could always pick a test point on the interval. So for instance, on this interval, you could pick a test point of 4.5 and plug it into each of the factors and get your sign. But the other way to do it is to look at the linear factors and determine which one gives the root that you're considering here. And so this one, the linear factor that gives the root 5 is 5 minus x. And a linear function will always change sign on either side of its root. So I know that it's going to change sign, and the others are going to stay the same. So this one will change sign, but these ones will not. And so that allows me to quickly determine the sign, because I'm going to still get a positive squared, but now this one is going to become positive, and on the denominator, I get a positive times a positive times a positive. Those will not change sign because 5 is not their root. And so the entire expression changes sign, and I get a positive. Now on the next interval, if I want to use that method, the linear factor that would change sign is this one, the x minus 4, and the others will not change sign. So again, I'm going to get a positive squared, and that one was supposed to be a cube. So I'll just erase that quickly. So that was a cube. And so here, as I was saying, I have a positive squared and then a positive cubed, and this is over. So this remains positive times a negative, because that one will switch sign because the 4 is its root. And so overall, I'm going to get a sign change, and I get a negative. And of course, you could pick a test point in the interval. A good test point would be 3. You could plug that in, and you would see that, again, you get a negative. Now, on the next interval, which one could possibly change sign? Well, this one could possibly change sign because 2 is its root, but then I'm squaring it, right? So the sign of the overall expression will remain the same, right? So this will be a negative, but then I'm squaring it, and then times a positive, and that's over a positive times a negative times a positive. So the overall sign will remain negative. Okay, because I'm squaring that. And then finally, the last linear factor to consider is the x plus 4, and the minus 4 gives the root of x plus 4, so that one will change sign, and so that's the only one that changes sign. I'm not squaring it or anything, and so the expression, the function, becomes positive. So now I've got the sign of the function on each of the intervals, and I would like to know when it's larger than or equal to 0. So that, of course, means I want to know when it's positive or greater than or equal to 0, and I can read that from my sign diagram. I can see that it's positive on this interval, and it's positive on that interval. So now I want to write out my solution. So my solution is, so it's positive from minus infinity to minus 4, but minus 4 absolutely cannot be included in the solution because it's not in the domain of the function. And it's also positive, again, on the interval 4, and again, I don't include the 4 because it's not in the domain of the function. And we go to 5 because it's positive on that interval. And now I am going to include the 5. And the reason I'm going to include the 5 is because that is a 0. And I wanted to know not just where this function was greater than 0, I also wanted to know where it was equal to 0. So I'm going to have a closed bracket there. And that's my solution.